plenary, which they will then present to this afternoon wrap-up session at 4 CES time, 4 o'clock in the afternoon, Central European time. Okay.
Thanks, Tommaso. I guess we'll just briefly introduce the session though while we're waiting here. So this is 10 years of operations, 11 now, and synergies with other Earth operations missions. So Monica Roca and I are going to be chairing this session. We have 5 talks scheduled, variety of talks here, but make sure you have the latest schedule download. There was some shifts in the talk, so yeah, make sure you have the latest schedule here. I think we should probably get started. Monica, do you want to?
I think we should get started, yes. So we have those 5 speakers. The first one is going to be Isabel Lawrence. So she's been also trying now the everything worked, and she will be presenting the emerged CryoSat Sentinel-3 freeboard products, its sensitivity to weather events, and what it can tell us about the KU radar penetration. So go ahead, Isabel.
Thank you, Monica, for that introduction. Yeah, it's quite a lengthy title. So good morning, everyone. I'm Isabel. I am a research fellow at the University of Leeds, and I'm going to be presenting this work that kind of started during my PhD, which I did at UCL with Michelle Samados and Julian Strover, and I've been doing little bits on it since being a research fellow at the University of Leeds, working with Andy Shepherd. I also just wanted to say thanks to Will Gregory, who's kind of advanced this work and has just published a paper on a merged daily CryoSat Sentinel-3 product. And I'd encourage you to check out his poster. It's number 143. And I also wanted to thank the ESA-GPod team, including Jerome Benveniste, Salvatore Donato, and Massimo Orlandi, who have done a lot of the low-level processing, so the level 0 to level 1B processing, and without whom this work wouldn't have been possible. So thanks to all of them. So the kind of the rationale for this work, or the incentive, I guess, was the launch of the Sentinel-3 satellite constellation. So it's an ESA and European Commission joint program. And Sentinel-3A launched in March 2016, and its twin 3B launched in April 2018. And there's 2 more, 3C and 3D, which are scheduled to launch in the coming years. And the reason they offer an exciting potential in terms of a synergy with CryoSat-2 is because they have a KU band radar altimeter, which is very similar in design and critically operates at the same frequency. Which means that we expect to get the same freeboard, and I'm going to explain what that means in the next slide. So I appreciate this isn't a CI session, so I thought I'd just give a little bit of background about some of the terms that I'm going to be talking about. So maybe some of you are familiar with the ice freeboard, sea ice freeboard. That's the height of the sea ice surface above the water level. When we're using radar altimetry, we also talk about the radar freeboard, and that's the difference in elevation between the sea surface and the height at which the dominant radar return is coming back from the surface. So when we convert radar freeboard into ice freeboard, we have to make assumptions about the radar penetration in the snowpack and also the depth and density of the snow layer. But if we just look at the radar freeboard on its own and assess, for example, what I'm going to show in this talk, the seasonal variability of the radar freeboard, we can potentially uncover things about the snow layer and about the radar penetration that we can't if we're using the ice freeboard, because we're already making assumptions about those things. So this is a paper that we published in 2019. It's actually just come out in print a few weeks ago. And this was kind of the original work to demonstrate that Sentinel-3 offered consistent freeboard results as CryoSat-2. And what we found in this paper, so we analysed a winter of data between November 2017 and April 2018. And we found this kind of quite consistent 1 centimeter offset on the radar freeboard. So Sentinel-3 was 1 centimeter higher. And I'm not going to go into too much detail. That you can read the paper if you want to know more. But essentially, we concluded that this was because of what we call a retracker bias, and the retracker bias being 1 centimeter different for Sentinel than it is for CryoSat-2. And essentially, the conclusion was that this extra centimeter needs to be subtracted from the Sentinel data to make it consistent with CryoSat-2. So in doing so, this is results from the subsequent winter, so 2018, 2019. And here I also included Sentinel-3B. So because Sentinel-3B launched in 2018, so this data was newly available for this winter. And by making that 1 centimeter correction, we were able to achieve really consistent results between Sentinel and CryoSat. You can barely distinguish the difference in the histograms here, and an overall mean difference of less than 3 millimeters, which is, very little, obviously. The other thing that was encouraging is that the standard deviation on the mean difference between Sentinel-A and Sentinel-B, 3A and 3B, sorry, was about 0.06, and it was consistent with the differences we found with Sentinel-3 in CryoSat or Sentinel-B in CryoSat. And that basically suggested that any differences we were finding between Sentinel and CryoSat were not to do with differences in the processing or biases, essentially, and was more to do with the fact that they are sampling different ice over the period of the month and kind of noise. So that was encouraging, that nothing was wrong with the way that we were processing the Sentinel data. So one of the reasons that it's important to have found consistency between Sentinel and CryoSat is because beyond the lifespan of CryoSat-2, this kind of means that Sentinel-3 will be able to continue the radar altimetry record, with the big caveat being that it only extends to 81.5, which you can see in this. Can you see my mouse, by the way? I don't know. Anyway.
Yes, we can. Yeah, we can.
Great. So yes, it doesn't have the full coverage of the Arctic Ocean, but at least below 81, it's going to be able to continue that record. But the other benefit, I guess, is that by combining the data from all 3 satellites, which is what these plots are showing. So this is just CryoSat on its own. This is passes within 1 month. Sorry, the labels have disappeared. This is Sentinel-A or Sentinel-B, and then this is the 3 combined, and you get a denser spatial sampling. And this plot on the right is showing that there's quite a lot going on, but if I just draw your eyes to these pink and yellow lines here, so the pink is showing 10 days of merged product. So the spatial coverage from 60 degrees latitude, north or south, will be the same. And the yellow dashed is the CryoSat-2 monthly product. So essentially what this is showing is that we can achieve the same spatial coverage as a percentage using 10 days of merged data as using a month of CryoSat data only. And that's great because that enables us to essentially start looking at variability on a much shorter timescale and more of a synoptic timescale, so timescale of which weather events might operate. So let me just, the first approach was to not do anything very fancy in terms of combining this data, so merging this data, but really just to treat all of the year-long track CryoSat and Sentinel data as the same data set and average it over an area. And the areas that we chose initially were the first-year ice and multi-year ice zones. And that's because we expect the signatures of radar freeboard to be different over the 2 because they have different snow layers and different roughness properties. So it kind of seemed like an obvious division over which to look at radar freeboard variability. So over these 2 areas, we averaged 9 days or 10 days of this merged product and the usual kind of 30-day CryoSat only product. And that's what these plots on the right are showing. So the dashed line is the 30-day running mean of CryoSat only. and the solid red line is the merged product, and that's the 9-10 day running mean. So what you can see is that there is this variability that isn't detected in the 30-day running mean. And the next thing to ascertain was to kind of try and figure out if this was physical and what might be causing it. So the first thing we did was we wanted to kind of separate the 9-day from the 30-day, or essentially look at the anomaly. Sorry, look at the variability in the 9-day signal alone. In a way, it's like detrending. So essentially, I subtracted the 9-day from the 30-day, and ended up with something like this. So I've called it the radar freeboard 9-day anomaly, but it's just removing that 30-day running mean. And this is what you're left with. And my initial thought was to maybe compare against something like snowfall, because we expect radar freeboard to vary with snowfall. So over those same multi-year ice, first-year ice regions, I averaged data from ERA 5 atmospheric reanalysis, and just one of their parameters is snowfall data. So average snowfall over those regions, did the same thing, the same kind of 9-day running mean, and ended up with this, which when I plotted it, I was quite surprised. A, to see such a strong correlation, so it's a correlation of 0.73, and also because what this shows is that radar freeboard is increasing with increasing snowfall. So our traditional assumption when we use KU band radar altimeters to derive sea ice thickness is that the KU band, the pulse penetrates through the snowpack to the snow ice interface. This is the assumption on which we base our sea ice thickness processing. And if this were true, or rather assuming this, we would expect radar freeboard to actually decrease with increasing snowfall. And there's two reasons for this. The first is a kind of physical reason, that increased snowfall will weigh down the sea ice flow, and it will reduce the ice freeboard, thereby also reducing the radar freeboard. And the second reason is illustrated in this slide, which is that the radar pulse is slowed by the presence of a snow layer. And when you're not assuming anything about the snow layer, this is perceived as, well, it equates to a longer travel time for the echo to return to the satellite, which is perceived as the surface being further away, i.e. the radar freeboard being smaller. So the thicker the snow layer, under the assumption that the pulse penetrates all the way through the snow layer, we expect the radar freeboard to be smaller. And that plot, so this plot here is seems to be showing the inverse to be true. So I repeated this analysis so this is the corresponding plot for the multi-year ice zone, and then we repeated it for the subsequent winter, 2019-20. And I guess the thing to say about these is the correlation is much poorer, but visually it still looks like there's quite a lot of correspondence between peaks in the snowfall data and the radar freeboard data, and none of the correlations are negative, I guess is, the point. This is making me think that maybe you need to do some kind of more advanced, this was just a Pearson correlation, but there are more advanced techniques for assessing the synchrony between time series, where you can account for things like lagging, and that's something to be investigated more, I think. So I wanted to just briefly have a look at ISAT-2, because obviously ISAT-2, we've seen some talks and we're much more confident, I guess, about where the ISAT-2 return is coming from the snow surface. And so with ISAT-2, we do expect the freeboard, that's the snow freeboard, to increase with snowfall. And that is what we see in this plot. So sorry, I should have said that ISAT is the blue here. And there isn't, again, there's not the ISAT-2 is correlated with the snowfall. It's 0.3 Pearson correlation. And it correlates, ISAT-2 correlates with our merged radar product with a Pearson correlation of 0.47. So again, this seems to indicate that CryoSat and ISAT are kind of behaving similarly in terms of their response to increased snow snowfall. So that was averaging over quite a large area. The next idea we had was to break that up into a kind of smaller space. So this is averaged on a 100-kilometer grid, and repeat the analysis. So just look at the 9-day running time series. This is for winter 2018-19, and you can see there's quite a lot of spatial variability, and there are some regions where the correlation is negative. So the highest for this winter was a positive correlation of 0.71 up in the high latitudes, and the highest negative correlation was 0.64, and you can see there that that's almost the behavior that we were more expecting to see. So it's interesting that there is this spatial variability, and it seems like at high latitudes the correlation is more positive, and in the peripheral seas there's more negative correlation, but I haven't explored that fully yet. The last thing was, so that was a spatial analysis, but it was over one winter, so it was fixed in time. The kind of last stage in this was to also see how it varies temporally. So it's again on a 100-kilometer grid, and I did a kind of running 14-day running mean of the correlation between the two. So the time series is essentially 14 days long, and it's running mean over the winter, if that makes sense. And so I'm just going to play this. I hope it renders okay. So what you can see, there's a lot of variability and what looks like kind of a lot of noise. But what I think is quite interesting, and this is, I mean, I only generated this last week, but there are times, so for example, if I just go back to here, this is kind of mid-March, and there's almost like this emergence of a really high, highly correlated region, and this is in the Beaufort Sea. And this is in March, so I was kind of thinking maybe this is like some kind of weather system, some kind of melt event that's essentially shifted the radar scattering horizon more towards the surface, and that's why we see this strong positive correlation in that region in that time. But yeah, there's definitely, that's my last slide. I'm just going to go to my summary. So there's more to be done in terms of figuring out what's driving these patterns that we're seeing. But I think it's quite a rich data set. I mean, I think it has the potential maybe to give us like a spatial and temporal metric for Ku-band radar penetration, for example. But there's a lot of there's a lot in there that needs analyzing in probably a more systematic way than I've done initially, including like multivariate analysis, and as I mentioned, a better way to assess the correlation between time series when there might be offset and stuff like that. So yeah, I'll end there. Happy to take questions. Thank you.
Thank you very much, Isabel. I think that we can now go through the questions on the chat, right?
Is that a question? Are you? Should I answer them in the chat? I can do that if we're running over time. I can't actually see the chat. I think I need to stop sharing my screen.
No, we have a minute or two, so we can try and answer. Shall I read the first question?
Yeah.
Well, thanks a lot. Sinead also says, thanks a lot for this lovely work and great presentation. Have you considered the impact of the ice drift as one of the reasons for the lower correlations, especially in the lower latitudes, peripheral seas?
Yeah, it's an interesting point. I mean, I guess, when I was in the second time series, when I'm taking 14 days, there's definitely going to be ice drift. Is definitely going to be a factor there, and it's not something I've yet thought about factoring in. Obviously, we have ice motion vectors, and it could come into the analysis. I mean, when I chose the initial multi-year ice, first-year ice masks, I chose pixels that were that ice type for the entire season to try and limit the effects of ice drift, basically. And that correlation for that season is better than any of the pixel-wise correlation. So maybe that's the reason. Maybe it's because ice drift was limited in that initial comparison. But yeah, it's an interesting point and something that definitely should be accounted for.
Good. I think Sinead is putting a thumb up. There's another question is, will the snow impact be different for different freeboard values? And can this explain the regional variability?
Yeah, definitely. So obviously, yeah, I mean, the bigger the freeboard, the less the same snowfall will weigh down the sea ice flow in a sense. And I guess one thing I haven't talked about is the fact that this over the season, the sea ice thickness is also going to be changing, and this is also going to affect the freeboard values. So, you know, when at the end I'm showing this map of the video of the variability, the temporal variability, to me that's suggesting that maybe this is showing variability in radar penetration, but it could also be showing the ice pack thinning and thickening in different regions and dynamics, as Sinead has already mentioned. So that there are a lot of factors that will influence the radar freeboard. It's not just the snow. And I guess the challenge is to kind of unpick all of it and, yeah, see if that's possible.
Good, thanks a lot. And finally, PSS, thanks a lot for the very good work, and that shows the potential of Sentinel-3 altimeter missions for measuring sea ice freeboard.
Thank you.
Okay, thanks a lot, Nathan. You want to present next?
Sure. So our next speaker is Paolo Cipollini. He's going to be talking to us about multi-band altimetry of the cryosphere. I believe Paolo is one of the new speakers for the session as well.
Oh, hello. Yes. Hello, everyone. Let me just share my video and launch the presentation. So, should be coming. Yes, there it is. This presentation is really a summary of a workshop that we had back in January, dual cryo workshop. And let me start from the introduction, explaining the motivation. We've seen this week, and we know that KU band altimetry, like the one that we get from CryoSat, has greatly advanced cryospheric science and is advancing cryospheric science. But we have also seen, and again, we've seen it this week with several presentations, that when you've got KU together with KA band altimetry, or you exploit KU together with laser altimetry, you learn more, essentially. So if you have a dual band approach, or even multi-band, which we can do because, as you see in this artist's impression, we go CryoSat alongside Altica and ISAT-2. Well, if you combine them all together, you learn more. And the new mission phase, Cryo-2-ICE, is a case in point, where we put CryoSat on this resonating orbit with ISAT-2 to exploit the data. And do not forget the Crystal, the Copernicus expansion mission, due to be launched in a few years' time, will be dual band, the KU and KA. We've got campaign data, but the campaign data have not certainly been explored and exploited in full. So there's a lot of potential for new findings exploiting a multi-band approach. Research is being carried out now. With all this in mind, a few months ago, within the Crystal MAG, the Mission Advisory Group, we had the idea that we really needed to sit and review the science that was available in view of the latest result. And the MAG, Crystal MAG, was a big promoter of this idea, especially Professor Andy Shepard. ESA was supportive of that, and we organized a dedicated workshop on dual band altimetry of the cryosphere, dual cryo, online, of course, back in January, with the objectives to review the state of the art, and dual band, and I could even say multi-band. You can use all three together. Identify the relevant campaign data, so from in situ data, airborne campaign, and satellite campaign, and discussing the processing of this data, what are the limitations of the algorithms, what we need to improve, what's the scientific readiness level of the different algorithms, so that we could identify gaps and make recommendations. So the workshop was broadly organized across 2 afternoons around the 2 themes of land ice, of sea ice. I should say 2 afternoons in European time, but some colleagues joined us at much more uncomfortable times of the day for them. So thanks to them. And the output of the workshop is a report that summarizes the state of the art. We are just formatting it. It's virtually ready. So I'll tell you more about this report, which hopefully might lead to a white paper. So we had this workshop organized by these people. Andy chaired it, and I co-chaired with the support from Gunther. Thanks, Gunther. And Mal, Macmillan, and Aero took upon themselves to lead and provide keynotes for land ice and sea ice and lead the sessions. And we had a good number of presentations, 18, with a lot of discussion. And we were pleased to see that a lot of people not just registered, more than 130, but we had more than 100 attending simultaneously each day. So in that respect, it was definitely a success. So what I'm going to show you very quickly in the next few slides is just a gallery of things that were shown. And we've seen some of them repeated or indeed extended in some of the presentations this week, because of course science and research will have advanced further since then. But just to give you a flavor of the variety and breadth of the presentations that we had. So we were looking at differences in waveforms, and not just amongst different bands, but even differences due to the different radar modes. Like here, you can compare CryoSat 2 pseudo resolution mode and CryoSat 2 SAR on the extremes, and Altica in Ka band, the low resolution mode in the middle. This is of Lake Vostok, which of course has emerged as a very nice area for investigation. It's very flat and with little surface roughness. And Jeremy Oblanc presented this data. So we were seeing differences and looking at differences, but obviously also looking at encouraging agreements in other places, or with different processing. So here you've got Sentinel-3A and B elevations against the laser elevations. Still, Lake Vostok and our CPOM colleagues have shown an excellent agreement. And in the past, because perhaps there wasn't much of an understanding of the processes, so people have been developing corrections with an empirical approach. Johan Nielsen, for instance, presented this work where they first retract CryoSat 2 with different retracting thresholds on the radar waveforms, and they investigate the sensitivity of these different thresholds to changes in some parameters. So essentially, the waveform parameters then are directly linked to changes in surface conditions, so they can be used as a proxy to describe the surface properties and derive an empirical correction that improves the things and that can account for things like the big melt event that we saw in the summer of 2012 in Greenland. We were shown by Tanya and Sinead and other colleagues all the different campaign datasets, very rich campaign datasets from CryoVex and ice bridge. Those data are there available, and that's dedicated websites. And we were reminded that a lot of these data still have not been exploited. So there's certainly clear need of providing tools and providing manpower so that we put to full fruition the investment that have been done into collecting those very rich data sets. And what we want to do at the end of the day is to start exploring the subsurface and understanding a bit better what's happening there. Ines presented, and she will have shown it again since then, these data from ASIRAS on the top panel and Karen, airborne data, one in KU band and the other in KA band over Greenland, where you see really the different scattering horizon with KU penetrating deeper and resolving really all the different layers, and note the higher scattering from the 2012 layer coming from that big melt event. And whereas in KA band we actually closer to the surface, but is it a reflection from, or a scattering from the surface? Not quite, because it's clear from discussion that we had that we need a model approach to interpret these data. And Ghislaine, for instance, from the SMRT model, which she has shown again this week, reminded us that, for instance, in KA band, there is indeed volume scattering, and it's quite large, but with a much less penetration depth than at the lower frequencies. And I can only see, in future, a much closer synergy and integration of observations and modeling to understand exactly what's going on. I should also mention these incredible results from Rosie and the Mosaic expedition from the Kuka radar, and Rosie has shown them again this week, where we see that cross-polarization changes the scattering horizon. And this is something that we really need to keep in mind when we're starting conceiving the missions of the future. Now, Crystal probably will not have such a cross-pol capability, but we need to start thinking what additional information and understanding will gain from trying to do something like this from space. So when you look at the HB channel, even in KA band, you start seeing there's no ice interface, which is amazing. Of course, we saw agreements and disagreements in trends. This is again from Ines, and the numbers that you got are the RMS between radar and laser data, and you see that KA and KU agree reasonably well in places, or they are quite different in other places. So there's more work to do, but quite a lot of effort. And Sebastian, like he has shown also in his talk this week, has done quite a painstakingly work of trying to reconcile all the different mass balances and bringing in all the different corrections and getting to what starts to be a reasonable good agreement for the Greenland ice sheet mass balance. Important item or topic for discussion was snow, particularly snow over sea ice. The principle of the measurement is from Ron Cox's presentation on the right, and we saw the interesting talk from Isabel just before mine. This is really an intriguing topic where we get the correlation of the opposite sign to what we expect. But so we need to exploit the data from KU band, KA band, and snow radar together, and we start seeing, you know, both the interfaces. So there's quite a lot of material for further investigations here. And some other data were presented by colleagues in AWI, where again, comparing the airborne laser scanner data in the ultra-wideband radar, we start elucidating what's going on in the vertical dimension quite nicely. So these are just quick examples of what we saw, and in terms of the discussion and the conclusions of land ice, of course, the holy grail is to gather reliable long-term estimates of surface elevation change and mass balance. We're getting there. We've seen a number of papers in recent years, and of course, I mean, what you want to do is to continue those and make them, continue those observations and make them better. From KU, we've done land ice elevation for many years. KA has got a shorter history. Now they're combined with laser, but until recently, the approach was to have these empirical corrections for the penetration bias, but we need a paradigm change where we exploit the differences to explore the subsurface, gain understanding on the subsurface. And there's a number of different effects to disentangle. I've listed them there. There's radar penetration, there's the terrain topography, there's the surface roughness, there's the spatial sampling bias. So you see the illustrated in that figure on the, you see the impact of the different SAR altimetry resolution cells in KU and KA of a complex topography. And the recommendation is that we need a study to consistently process all the three bands from airborne and satellite data over some test sites, and bringing in modeling as needed. So it could be the Amundsen Sea or Northwest Greenland, or even Mountain Glacier location. Do not forget one of the objectives of CRYSTAL will be really monitoring of glaciers. Look at my last bullet point. We really need a range of retracking approaches. So we need to put efforts now on retracking, because the retracking defines the retrieval and the quality, and we need to explore the trailing edge, of course, if we want to get a hunch on the subsurface. For sea ice, KU band retrievals are mature, KA band less mature, but of course, much work remains to be done on dual frequency for snow thickness retrieval. And for KA band, when we'll get KA band data in SAR mode from CRYSTAL, we'll have to learn a few new things because we don't have experience on SAR altimetry mode in KA band. Of course, there's lots of benefits from using the three bands together, including the fact that with the laser altimetry, you get a nice description of the surface roughness, which is useful. Again, retracking is a key aspect here, and the volume scattering should be exploited further. The recommendations, again, are for a dedicated sea ice KA-KU laser study. It requires manpower, even if it is just to fully exploit the many data from campaigns that we got already in the archives. We need to put resources there in terms of tools and manpower, and retracking will need some work. And future campaigns, of course, need to be organized and synchronized with the cryo to ice overpasses of CryoSat and IceSat 2. It's important to to invest also in measurements that describe the interface between the snow and the ice, and those measurements are intensive, time-consuming. Sorry for the typo, and manpower intensive. So the overall conclusions from the workshop was that we really need multi-band altimetry to characterize the subsurface structures and the snow properties, but we really need more work on the algorithms, on the tracking, and modeling will help and must help. At the moment, we are discussing on whether to develop a KU plus KER new airborne instrument, which in combination with a laser would greatly help with future campaigns. The workshop, however, overall consolidated really the science case for dual band altimetry from crystal, and hopefully it will have promoted, and the results will continue to promote the timely and rapid implementation of crystal. I know this is something on which Andy and the whole crystal mag are particularly sensitive, and of course they've got all my support. This is particularly important because, of course, we've got a prospect of a gap in polar observation. We don't want to delay crystal any further. We want to put in orbit as soon as possible. And I'll just conclude by reminding you that there's a website with all presentations of the workshop. The web address is a little bit longer, so you just Google dual cryo, you'll find it nicely. And I will put the final report in the next few days there, and then we'll see how to continue with a white paper if it is feasible. Thank you.
Thank you, Paulo. Don't see any questions in the chat right now. Oh, quick question from Sarah Fleury. See, a comment. Also need for snow radar airborne data for validation of the altimetric differences. So
yes,
nice
it's a very good point. Yes, I would agree. In fact, the data that we've got already from the ultra wideband radars are quite valuable and rich. So we need to continue those observations. Thank you, Sarah.
Okay. Thank you. And okay, let's move on to our next speaker, please.
We go to the next speaker. And it's Laurent Rey. Laurent Rey, I hope he's in. And he will be presenting CIRAL or CIRAL, depending where you're from the early design to 10 years of in-flight monitoring and its contribution for future altimetry development. Is Laurent Rey?
Yes. Do you hear me?
Yes, we do. Good morning.
Hello,
Laurent.
Monica.
Hello. All yours.
So I share. Do you see the screen?
Not yet myself. I still see you.
I share. Okay, I try to share the content. It's connecting.
You had the button activated, right?
Yes.
You could share. All right.
Do you see the presentation?
No, not yet.
We had a problem sharing your content. Try again later. I try again.
Do you want me to present on your behalf, Laurent?
Sorry?
Do you want me to present on your behalf? And you just tell me next.
The problem will be the same, I think, because
Well, he's the host.
yes. Once I put share, it said we had a problem to share. Do
I'll
you have
share it for you. You send us the presentation so I can do that for you.
Yeah, that's fine. So hello everybody. I will tell you about from the early design of CRL, the instrument of CryoSat, to the 10 years of in-flight monitoring. Next slide, please. So back to year 2000. At this time, the instrument we had in flight, or quite ready to be flight, was on JSON-1, and it was a pulse limited conventional radar. Next slide, please. And for CryoSat, we had to design a new concept of altimeter based on unfocused star radar. Next. Next slide, please. So meaning that we had to synchronize all the received echoes and to make it a coherent instrument. Next. And also we had to add a new functionality, which was interferometry radar. Next. Meaning that we need two receive chain to operate interferometry. Next. From in conventional altimeter, we added the capability to have accurate knowledge of delay inside the instrument, less than 50 picoseconds. This was the baseline we take from Poseidon 2 to design a SAROL. But we had also a new challenge. Next, please. We had also to design an instrument where we knew really the phase behavior with an accuracy of less than 0.1 degree. For that, we put inside the instrument several calibration modes to expect that we can foresee the evolution of the instrument during the lifetime. Next. Again, back to year 2000. The instrument we made on JSON-1 was a single transmit-receive antenna. Next. And we had to put in addition a receive antenna for the interferometry on a ultra-stable base plate. Next. Instead, to ensure a stability of angle of arrival of less than 0.007 degree. And for that, it was necessary to develop a test facility to measure accurately the wave angle of our characteristics. Next. Again, back to year 2000. JSON instrument was using a tracker over ocean surface, so a surface quite monotone. Next, for CryoSat, we had to put in addition a tracker over ice with a high dynamic signal, and also a tracker over land ice with an altitude variation from 0 to 5,000 meter altitude. So we made, with the support of CNES, two new types of algorithms with big simulation to try to find where the worst case over the globe, to allow that the instrument will track in any conditions. Next. This is the student. You have the classroom of all people which participate of this adventure during the CryoSat 1 mission. Next. Now we switch to in-flight operations. In-flight operations, you have here the 1 month of operation of SARAL, the instrument. You see that SARIN, which is interferometric mode, SAR mode, which is a high resolution mode, and low LRM, which is a low resolution mode, are operating quite all the time. And sometimes there is some calibration, like calibration 2 for to see how the instrument is operating in the bandwidth where the echo can shift, and also to have all the characteristics of the electronic with the calibration 1. There is also an indication here. It is the mode where we acquire the echo, which is the acquisition. And next slide, next. We see how much each mode is operated during 1 month. So meaning that interferometric is about 13%, high resolution is about 20%, and low resolution mode is 70%. And the acquisition is about 1%. So meaning that the algorithm to track the echo is quite performant, because we are not losing a lot of echoes during the operations. This number are mainly dimensioned for the memory in flight. They have been changing during the mission. SAR mode, which is the high resolution mode, was increased. There is no limitation on the instrument, and we can change this figure if we need it, and if also we have the capacity to download the measure on ground. Next. The acquisition mode, if you see how it operates, you have the measure on the left, where you see that during October up to April, it is higher than the other period from April to September. We have not the reason of this quite small evolution, because it's all the time around 1% of the time during the months. But one reason could be that on the north side of the globe there is the Arctic shape, which is evolving with a higher surface to cover. Next. In flight behavior also, we can see the antenna temperature evolution. On blue, it is the difference between right and left antenna, and in green and yellow, this is each antenna evolution. With this characteristic, we can see where the instrument is put in standby mode, mainly to avoidance of collision maneuver. And we see that the antenna temperature evolution is lower than what we expected, up to 19 degrees down to minus 19 degrees. So meaning that the instrument measurements are in a region where the instrument is quite stable and more stable than we expected. Next. Another in-flight behavior which was not foreseen to be measured, it is side of the instrument, which is the impact of radiation in flight. And we can count with the instrument the error of memory. We have a component which corrects the errors. And once he corrects the errors, he send a message. And during the 10 years of measurement, we have seen about 2 radiation errors per day with maximum of 8. And studies showed that we can divided this error into 2 types of error. The cosmic rays, and you see on the right side the curve, and the upper curve is the cosmic rays, and you can see slightly the cosmic rays and the cycle of the cosmic rays coming from the sun, which is a little curve, and also the wrapped proton, which is about 1.6 per day. And you see on the left figure where the maximum events are occurring, but we know already that it's around the South America. Next. In flight performance, as you may know that we have a lot of measurement with the calibration, which ensure that the instrument is well known during the operations. And in particular, we have a mode which is operated during interferometric mode, which allows to place some calibration impulse during the tracking of the echoes. And what we see that in flight, all the calibration shows that the delay evolution inside the instrument is less than 20 picoseconds. This delay is not taking into account the field up to the antenna, but it takes about 90% of the contribution of the instrument. And there is also a parameter which is a float, which is the radar resolution, which over 11 years had no evolution. Next. In flight also, we have seen some characteristics. We have also on Sentinel-3, and we see that the power and gain is evolving, and slightly evolving more on over the 3 first years, with about 1.9 dB on the total over the period from October 2010 to now. During the last years, 7 last years, the curve is smoothly coming to a stabilization, and now we are about 0.01 dB per month trend. So this is very slow, And there is no problem for the instrument because there is sufficient margin and for all the mode, and especially the most affected could be the low resolution mode. All the other modes are with high margins. There is no problem for the instrument to continue for 4 years with this behavior. This behavior is measured on flight. We can correct. There is no problem on the data. Next. The other performance we measure in flight is phase difference, so the interferometry inside the instrument. And on the upper curve, we have the temperature difference between the two receive chain evolution. You see the evolution inside the instrument. And on the down the other curve, which is on the bottom, there is the phase difference evolution of the instrument, which is measured during interferometry mode. Next. We can see that some events on temperature is directly correlated with the phase difference. Some are not, but you see on this graph the life of the instrument. Meaning what? Meaning that sometimes for maneuver, the instrument is stopped and start again, and the stabilization takes time. So that's why some events cannot be correlated directly with the temperature evolution. But once the instrument is in operation, you see directly the correlation between temperature evolution and phase difference, so interferometry phase inside the instrument. Next. So in-flight differential phase calibration is a trend about 0.06 degree per month, so very, very, very slow. We can make the instrument like a measurement of thermal behavior of the instrument. About 1 degree thermal difference between a receive chain is about 2 degree phase difference directly. Next. So CryoSat instrument, where we are still on the operating nominal chain. We have not switched to the other chain, so there is still a lot of time for the instrument to be operated without any real big problem. Next. It opens the ways SRL to high resolution altimetry. Now SRAL on Sentinel-3 and Poseidon-4 on Sentinel-6 has adopted this mode and also enhanced this mode. Large swath altimetry, carrying RFU SWAT, and now large swath altimeter. These elements have been given by Laurent Philippou yesterday with such a lot of detail on the enhancements we have obtained. And the last one is a B-band KUK band altimeter for snow detection, the risk crystal. Next. As you know, and which is already discussed, this instrument will allow, in addition with other enhancements, very big enhancements like fully focused mode. It allows to detect the snow and the ice contribution to the volume of ice over sea ice and also on inland. Next. So CryoSat was an unforgettable experience for us here in Thales. all people which talk about this this program has really light in the eyes, and it was really a fantastic community. Next, we had several times where we shared together, ESA, Airbus, and us. Very good moments, like here. After the CryoSat failure, we were motivated to relaunch CryoSat 2 next. A very good moment also in, on the when we were on the commissioning phase. And next, and recently, in March 2019, we meet together, Airbus, ESA, and us. Very good moments. Thank you very much.
Thank you very much, Laurent. It's very nice presentation, but very nice end of the presentation when we see all these memories of a really nice satellite indeed, a nice project that we've all enjoyed a lot, and now we are still enjoying all the results that's still providing. Thanks a lot. I don't see any questions in the chat. I could have some, but maybe because we are over time, I would probably pass the next speaker, unless someone is asking something soon. Otherwise, thanks a lot, Laurent. We move to the next speaker. Thank you.
Thank you. Bye bye.
All right. Our next speaker is Mark Nige. He's going to be talking to us about CryoSat long-term ocean data analysis and validation.
Okay, good morning. Thank you for the introduction. My name is Mark Nige. The only question I have now is are my slides visible in full screen? And can I be heard? Well, I see people nodding, so that's good. So let's have a start at this. I am kind of the stranger here because I'm going to talk about ocean applications, and most of the talks, I think, yeah, of course, CryoSat, I have to admit, is a fantastic cryosphere ice mission. So, and it has proved to be that. On the other hand, it is also a fantastic ocean altimeter. And I will try with this presentation to emphasize that. So yes, this is part of a project that actually looks indeed at the ocean application of CryoSat altimeter data, and there are questions like how stable is the platform? Can we use the altimeter data has it such an accuracy and also drift that it can be used as an essential climate variable, and those kind of questions. So in our project, we have a few objectives: long-term analysis, validation of the CryoSat 2, level 2 baseline sea altimeter geophysical ocean product. So this is what is referred to as the GOP product. So we like to assess the quality, the consistency, stability of the GOP parameters, and of course we have an emphasis on sea level measurement and orbital heights. We compare with concurrent in situ data, so tide gauges, transponders, etc. We compare with relevant ocean and meteorological models, and we also compare with other altimeter datasets available through the radar altimeter database system RADS. Now, contents of this talk, actually two of these objectives we saw on the previous slides, we will talk a little bit in more detail. So we have CryoSat 2 and concurrent altimetry and RADS, and we have CryoSat 2 and concurrent in situ data. Data handling, the treatment of the data as well. We want to compare with all the other data we have in RADS, so we really have to put it in RADS format. So we need a bit of changes there, not too much, because we want also to stay close as possible to the original product. So data available at the time of the start of this analysis, I think most up to almost the end of 2020, and that was already 3 years more than baseline B. So that is what our focus on baseline C. What do? We reference the orbital altitude, the geoid mean sea surface, where we go from the WGS 84 to the TOPEX ellipsoid, because that is the REDS standard. And we extract the ocean tide by subtracting low tide from the ocean tide solution in the COP product. We have to do it a bit different for the GOT 410 and also for the FES 14. Okay, so for now, these details are not that important. There was one problem with the ascending flag that cannot be considered reliable in the current baseline C product. We replaced it by just checking the latitudes of the first and last measurement, also, of course, to get an idea of whether it's ascending or descending. First step in this analysis was actually to compare all the corrections in the GOP data, the corrections you need to arrive at sea level anomaly. And how did we do that? We validated these corrections by generating GOP RADS enhanced data. So actually we used the tools in RADS to generate the corrections according to RADS, but also according to the models that are used in the GOP product. And then we, of course, start comparing what is in the GOP product and what is generated by our RADS tools. So we intercompare the RADS corrections with the GOP corrections. Now, most of the differences, fortunately, exhibit the expected outcome. And the GOP corrections have a 1 millimeter precision. RADS has internally 0.1 millimeter precision. So any difference, if you have exactly the same model, if you have exactly the same proper interpolation, would exhibit random steps between -0.5 and 0.5 millimeters, or from 0 to 1 millimeter, something like what is plotted on the right plot on this page. So here we have the dynamic atmosphere correction, both for what is in GOP and what was generated by our RADS. Now, not all of these corrections behave the same. Interestingly, the ionosphere correction based on GIM, and that is both for what is in GOP and what is generated by RADS, they show a different behavior than this stepwise 1 millimeter, let's call it noise. And in excess of a few centimeters. So look at the top left. So this is just for APAS, an example how the GIM differences between GOP and RADS. So that is, of course, a bit strange. If you plot them separately, so that's the top right figure. The blue is the original iono, so that is in the GOP, and in the red we have the ionosphere correction according to RADS. Now, if you have different let's say different models, you could expect maybe a difference like this, but not if you have the same models. So this is something at the moment we still have to investigate. It is currently undecided which solution is the one or is the better one, but at least we have seen that there is a difference. Two other corrections that also raises a bit of a concern. So we have the finite element solution ocean tide difference. That is the bottom left. There we have some kind of a zigzag pattern, and the differences within the DTU 15 mean sea surface, that's bottom right. It's quite noisy, quite high compared to what we get for if we compare the CLS 15 solution. The noise is twice as much. Now, this is still the let's say the corrections to visualize the differences geographically. We have applied a collinear analysis and then again comparing GOP and equivalent RADS corrections. And typically, if there's no problem, let's say, with the corrections, then you would end up with a figure like the top left. So that's again for the inverse barometer, or sorry, the dynamic atmospheric correction, but there are more corrections that behave like this. I only plotted the rest of the figures, the ones that have some special patterns, or still give us a kind of a headache. We have pole tide difference. That's the top right. It's a very typical spatial low harmonic difference. So this might imply that we still talk about different models, though by name it's the same. But of course there is some issue whether it's static or dynamic. But okay, if you look at the numbers, these are quite small. We have the finite element solution 14 difference, bottom left. Some interpolation artifacts, so that these are the blue and the red stripes. But okay, again, the most concerning is the GIM ionosphere difference. And we plot the difference, but actually what you see in the difference is the signal of the ionosphere correction itself. So this is really something we still have to find out what is going on here. We see the differences, though all the documentation suggests we have identical models. I think the most important question, if we talk about the differences in corrections, do these correction differences affect the data stability, or are they causing any drift and would end up in some kind of maybe a sea level trend analysis? So we again difference the correction data in a collinearly manner and average them per cycle, and then monitor them cycle by cycle. So just to see whether there's some periodicity and trend. So all results of all our corrections are shown here: dry, wet, ionosphere, dynamic, solid tide, pole tides, ocean tides, ocean load tides, etc., etc. Now, I think basically, if you look at all these, okay, added on the bottom is sea state bias. So there is some trend in sea state bias difference, but the conclusion actually is, fortunately, all corrections don't seem to contribute substantially to the observed trends in sea level anomaly. So there's no direct effect on long-term stability. Only the ionosphere and the sea state bias seem to have a traceable trend, albeit all in the order of smaller than a few hundreds of millimeters. So I would say we started off with a bit of bad news, but I think this is good news. So let's try now to compare what we have in reds, and the basic tool for that would be or is crossover analysis. So here we cross the GOP passes with JSON2, JSON3, Sentinel-3A, Sentinel-3B, Soral. We have also Soral in the repeat mission and Soral in the geodetic mission. And we have our own CryoSat. Well, let's say at that moment, we also have our own CryoSat dataset, so we also compare it directly with the REDS CryoSat. Some details about the crossovers. Maximum crossover time difference is 5 days. I would say normally you would use something like 1 or 2 days, but yeah, well, of course, CryoSat is in quite a high inclination orbit. You would still need this 5 days to give sufficient crossovers for proper analysis. Increased ocean surface variability is bypassed. We do a very rigorous crossover difference edit. Everything more than 1 time the standard deviation is discarded. Well, that actually only discards 15% of the data, so it's not that bad. And to exclude sea ice areas, sorry, so no ice here. We limit our analysis to 70 degrees north and south. And so yes, this excludes the high number of crossovers in the polar regions, which otherwise also would bias actually a little bit your crossover analysis. Talking about the difference, so when we compare CryoSat 2 with JSON2, for instance, and the crossover difference between CryoSat and JSON2, that gives the range bias with respect to JSON2, so the range bias of the CryoSat with respect to JSON2. But in REDS, the data is all referenced to the topic reference, and we also applied a calibrated range bias to all the missions. So basically, the actual range bias is with respect to the topos reference and can be considered the absolute bias. And then you get plots like this. So here we have the examples of sea level anomaly, significant wave heights, sigma naught, wind speed, and sea state bias of CryoSat GOP data with respect to JSON2. And this is geographical distribution of the mean crossover differences between these satellites, and we do that for these 5 altimeter parameters. And of course, then you get an idea of patterns. In the end, you want to have some kind of a mean to say something about biases. And then we can, of course, I will not go through this table in detail, but we have the top table, is the dual satellite crossover, where we crossing, for instance, the first row, JSON2, that is JSON2 crossed with the GOP CryoSat data. So top panel is the dual crossovers. I think that is the most important panel. So and then below is the single crossover statistics. So for crossing ascending and descending passes. So what are the things to pay attention to? For instance, if we look at this mean value SLA with respect to J2, so the very first number we see is 2.82 centimeters. That is the absolute bias we get. Well, if we compare with JSON2, we compare with all the other satellites. You can actually take an average there. That would be something like 2.9 centimeter, what is still left as a bias in the data. And somewhat more interesting things, well, but that's too much time, I guess, to go over more. Sorry, more of these numbers, but okay. So what are we looking here at? This is a look at the different biases, how they evolve over time. So you see these plots before, but now we do that per cycle, or actually over time. It's I think in the interval of 2 weeks. So again, comparing CryoSat with JSON2, for instance, but also with JSON3, all the other satellites. So top left is what we call the range bias. So now we have it over time, so you can also see what is happening in terms of periodicity and also in terms of trend. For instance, the light blue, well, not the lightest blue, but let's say the first line was with respect to J2. We see again this 2.82 centimeter bias, and we see also a trend of 0.1 millimeters per year. Now we do this, we have this for we have the standard deviation top right. So sort of crossover RMS, let's say evolving over time with respect to all the other satellites. And we also have the sea state bias, wave height, and sigma naught and wind speed. I think here the most important thing is this number of 0.1 millimeters per year. And so in the top left, the SLA range bias of GOP with respect to JSON2, the blue curve averages to minus 2.82 centimeter with a drift of 0.1 millimeters per year. Actually, we did that also for baseline B, and then it was 0.14. So we also see kind of an improvement there. I would say this is an excellent result. Also significantly better than what we call the SLA, essential applying variable constraint of being better than 0.5 millimeters per year. 0.1 is indeed better than this 0.5 millimeters per year. And it's certainly on par with the current uncertainties in the sea level trend estimates. So some conclusions, recommendations concerning the baseline C, the ocean product for CryoSat. More than 10 years worth of GOP data compares very well with JSON2 and JSON3, as those are what is called our reference altimeter missions, and it's very well suited for oceanographic applications. The data also compares well with Sentinel-3AB, Seral, and what we had in rats for CryoSat 2. We see a slowly increasing timing error, but also nothing to worry about, I guess. This erroneous sending flag. We do have a few minor problems with the corrections. And I would say, if you use the data, the baseline C as it is for sea level anomaly, I would recommend using the ocean tide GOT 410 and the mean sea surface CLS 15. So none of the corrections deviations contribute to the overall observed trends. And we have a range bias of minus 2.8 centimeter. If we average that over all our satellite missions, it is minus 2.9. And okay, that ends actually the part on concurrent altimetry. Not sure about the time. There's still some time left. Then I don't hear anything, so I'll just continue. This is a bit shorter story. This is comparing altimetry and tide gauges. What we do, we apply all the standard corrections to the GOP and also to our altimeter data, to the RAS altimeter data. So that is the GOT 410, that is the CLS 15. And the only thing is what we do differently in our normal analysis is that we, for the dynamic atmosphere correction, we only apply the high frequency part. So let's say the MOG2D, meaning that we do not apply static inversion barometer effect, as it is also not applied to tide gauge data. Then we grid SLAs to obtain monthly solutions. So this is a bit about the gridding. And then we compare, and then we remove a common bias because the tide gauge data are normally not referenced to a known ellipsoid, but rather to a locally defined mean sea level. So for the comparison, we use the PMSL data. We select data for the years 2010 up to including 2019. So that reduced the data set from around 1,500 gauges to 500. Then we only consider tide gauge stations with, let's say, quite high correlations, larger than 0.7, the standard deviation between the tide gauge and the altimeter data of better than 15 centimeter. And we also take care that there's not a too big slope between them, because that could point to a local phenomenon like land rise or land some seismic things also happening. So we just make sure that also the slope is within certain bounds, so that's a centimeter per year. So that reduces the data set further to 185 tide gauges. You will see the locations on the plots. And then we just start comparing. So here we have the CryoSat GOP data. So that's the CG standing for CryoSat GOP minus the tide gauges. We have a correlation of 0.84, standard deviation of 5.8 centimeter, average over all these tide gauges, and a tilt of minus 0.19. I've introduced mean rate of sea level change due to global isostatic adjustment, being about minus 0.3 millimeter per year. The bias drift becomes 0.11 millimeters per year. That is more or less corresponds with what we have found before. And then we also see that actually the CryoSat 2, as we have it in our RAS database, is performing slightly worse, I would say.
Thank you, Mark. At this point, I think we're pretty far over our session time, our session time. If you could give a brief statement, though, to wrap this up.
Yeah, I will wrap this up. So this is some conclusion recommendations for the tide gauges. We have seen the numbers. I think, yeah. So this is also what I said. We see RATS, or let's say the GOP original product, performing better than the RATS CryoSat 2 products. There is a caveat here, or not a caveat, but a footnote. And it says recently in RATS, the RATS CryoSat 2 data has been replaced by the GOP baseline C data, as it was indeed appreciated how well the data is. And this was also partly because of our analysis. So we do have baseline C data in RATS nowadays. be it with REDS corrections. That is, well, that's what I wanted to add. So very quickly, some acknowledgements. Thanks go to the Strong Go Far, ESA, for supporting this research, to the whole GOP team for a splendid CryoSat data product, to Tommaso Parnello for managing a fantastic mission, to Duncan Wingham for proposing the CryoSat mission, and last but not least, also thanks to Remco and Eric for their continuous maintenance of radar altimeter database system REDS. Sorry for this commercial at the end, but this is it. Thank you.
Thank you, Mark. And yes, indeed, thank you to everyone. It looks like the results of all this are pretty good. Happy to see all this. See, Jerome put that the next baseline D is planned for 2022, so several upgrades there. For now, let's move on to our final speaker, shifting gears a bit more. So Niels Olsen will speak to us about exploring Earth's magnetic field and environment with CryoSat 2.
Yes, hello everybody. Can you see my screen?
Yep.
Yes. Okay, you may never heard about before using CryoSat for exploring Earth's magnetic field. But incidentally, if you look at the logo of this science conference, this is exactly pinpointing what this is about. Using CryoSat for exploring Earth's magnetic field. And in my talk, I will first give a short introduction to the different sources to Earth's magnetic field. Then we will look at why are we using CryoSat, how have we done that, and finally some applications. I would like to take the opportunity to thank a few of you who have contributed to this very exciting experiment of using or misusing the CryoSat mission. So why can we do that? Well, most satellites, including CryoSat, they carry magnetometers for navigational purposes as part of their attitude and orbit control system. That's the so-called AOCS. And the data of these AOCS magnetometers, they have scientific values. We can use them for geophysical explorations, but they need a careful calibration. And if we then combine the data from these so-called platform magnetometer satellites like CryoSat with data or with simultaneous measurements from dedicated missions to explore Earth's magnetic field like SWARM, then we get a true swarm of satellites to explore the Earth's magnetic field. So let's start and look at what are the different sources to Earth's magnetic field. Well, we have the interaction between the solar wind and the Earth's internal magnetic field. This gives some electric currents in the ionosphere and in the magnetosphere. These are the so-called external field. And then we have the internal sources. And the internal sources, there we have magnetized rocks in the crust. The metal is non-magnetic, but the main part of Earth's magnetic field is due movement of molten iron in the fluid outer core. So if we summarize that, we have magnetized rocks in the crust, and we have movement of molten iron in the fluid outer core. That means at a depth of about 3,000 kilometers. Looking at the internal sources, by far the largest part of the Earth's magnetic field, about 94%, is due to sources in the core. And sources in the crust is only weak, it's about 3%, but it's very depending on where you are on Earth. These are the internal sources. And in addition to that, we have the external sources. These are the current systems in the ionosphere and magnetosphere. That means at altitudes above 100 kilometers or so. On average, their contribution is also weak, about 3%, but they are highly dynamic and unchanging. So if we're talking about dedicated satellites for exploring the Earth's magnetic field, this started about 60 years ago with the POGO satellites, and then we had the MaxSat satellite. And after MaxSat, that means after 1980, we had a gap of almost 20 years until the launch of the EarthSat satellite, and then JAMP and SAC-C 1 year later. And then since 2013, we have the swarm satellite mission, which consists of 3 identical satellites, 2 of which are flying side by side at a somehow lower altitude, presently 430 kilometers. And then we have a third satellite flying at a higher altitude, presently 530 kilometers, and in a different orbit plane. So, with all these dedicated satellite missions, why are we interested in using CryoSat? Well, if we look at the last 20 years of data, we had Ørsted, Saxi, and CHAMP. But as you can see, we had the atmospheric re-entry of the CHAMP satellite in the second half of 2010, while we have the launch of the Swarm satellite trio in November 2013. That means we have a gap of almost 3 years between CHAMP and Swarm. And here the CryoSat comes into play, because CryoSat helps to fill this gap for improved study of the dynamics of Earth's core field. How is Earth's core field changing in time within these M3 within these M3 years? That's one of the reasons why we want to use CryoSat. Another reason is the sampling. If you take one single satellite, and in this example I've taken CryoSat, and you look at the data coverage that we have, if you take only 1 day worth of data, well, we have a fairly good description, or we have a fairly good coverage in the Earth fixed frame. And the internal sources, that is core field and crustal field, they are fixed to an Earth fixed frame. But the external sources are fixed to a sun fixed frame. And with only 1 satellite, we have a rather limited coverage in a sun fixed frame. And this does not improve very much if we take 1 month worth of data. Then, of course, we have an excellent coverage in the Earth fixed frame, but still not a good coverage in a sun fixed frame. This is if we have only 1 satellite. But if we now combine data from different satellites, and what you see here is the local time drift of the 3 Swarm satellites in red and blue, and of CryoSat in yellow. And you can see from time to time, we have really excellent global coverage in local time if we combine data from all these satellites. You can also see that here on the left-hand side, we have Swarm alone. So here we had the higher satellite. Here we have these a pair of 2 satellites. And if you combine that with data from CryoSat, and in this case also from another satellite called CSES, which is a Chinese satellite, then we get a much better simultaneous observation of the Earth's magnetic field at different local times. Okay, so what are the secret instruments of CryoSat that allow to do that? Well, there are these 3 flux gate magnetometers as part of the OCS system. And each of these flux gate magnetometers measure the 3 components of the Earth's magnetic field vector. And then, of course, we have the 3 star imagers. So in order to do this, we need to calibrate the output of the flux gate magnetometer. We need the raw sensor output from the flux gate magnetometers. We also need the quaternions from the star imager. And in order to calibrate it, we need model values of the magnetic field at satellite position and time. And that's one of the differences between satellite like CryoSat and a dedicated mission like Swarm. Because on Swarm, we also have an absolute instrument. This absolute instrument only measures the magnetic field intensity, but we can use that in order to calibrate the vector instrument on Swarm. We don't have that on a satellite like CryoSat, so we need an external magnetic field model in order to calibrate the data. The data that are presently available are 4-second sample, and it's spanning almost 10 years. So it's from beginning of mission until end of 2018. So let's look at how have we done that. Well, in order to calibrate a magnetometer, each magnetometer has 3 sensors. That means 3 axes. And each of these 3 axes has a bias. So we have 3 biases. Each has a scale value that we have to estimate. So we have 3 scale values. And then we also have to estimate 3 non-orthogonalities in order to transform from the non-orthogonal sensor system to an orthogonal instrument system. In addition to that, we also have to account for alignment. That is described by 3 Euler angles, which describes the rotation from the magnetometer frame to the star imager frame. Okay, so in total we have these 12 parameters, and they are estimated by a least square approach by comparing with the field model. In practice, it's slightly more complicated because these calibration parameters, they change with time. So we do that by estimating them separately for each of the we do that by estimating them in bins of 1 month length. We have 100 months worth of data. So in total, that means we have 1,200 model parameters. In addition to that, we also have to account for some temperature dependence of offsets and scale values. We have to account for disturbances by magnetometer action, disturbances by solar array and battery currents, and we also account for some crosstalk, some non-linearities of the sensor. So in total, we have about a little more than 1,200 model parameters, and which we estimate based on 13 million data points. Okay, let's now look at some of these observations. What you see here is the observed magnetic field intensity for swarm and for CryoSat. And the magnetic field is strongest near the poles. There is about 50,000 nanotesla, and it's weakest near the equator. That's only about 25,000 nanotesla. And you can also see that there's one region of, in particular, weak magnetic field. We have seen that also in one of the previous talks. That's the South Atlantic anomaly. You can also see that the magnetic field at CryoSat altitude is weaker compared to swarm because we are at a higher altitude. So these are the observations. And if you then compare that with the model values, well, on this scale, we hardly see any difference. But if you now take the difference between observations and model values, you can see on the left-hand side for swarm, we have a fairly good agreement. At non-polar latitudes, the differences are less than 5 nanotesla. We have some deviations at polar latitudes. This is expected because these are the polar ionosphere currents. They are so dynamic that they are presently not covered by any magnetic field model, and therefore they show up in the data. But for CryoSat, if we just use the uncalibrated data, we see differences up to 100 nanotesla and more. But if we then apply the calibration, the situation is quite different, and we get field values which are comparable to what we see with swarm, almost comparable. We also see these effect of polar ionosphere currents. They are weaker in CryoSat because we are at a higher altitude. We are further away from these ionosphere currents. Perhaps this is also, if we look at the magnetic field differences in dependence on magnetic latitude. So on the left-hand side of each of these panels, you have the South Pole, the magnetic South Pole. In the middle, you have the magnetic equator. On the right-hand side, you have the magnetic North Pole. And we can see that for swarm, we have at known polar latitudes, we have an RMS of below 2 nanotesla. So that's the modeling uncertainty. We have a measurement error, which is much better, which is about half a nanotesla. For CryoSat, at non-polar latitudes, we have an RMS of 6 nanotesla, which is not as good as swarm, but it's remarkably good. And of course, at high latitudes, we have further disturbances due to these polar ionosphere currents. So let's now look at the first application, and that is monitoring the magnetospheric ring current. If you go to the equatorial plane at a distance of a few Earth radii, let's say 6 to 8 Earth radii, then we have a giant westward and directed electric current. That's the so-called magnetospheric ring current. This is responsible for geomagnetic storms. And this magnetospheric ring current is very dynamic, and it changes with time. And what you see here is 2 months worth of data. where we have estimated the strength of the magnetic spherical ring current hour by hour by using magnetic data from the different satellites, including CryoSat, shown in yellow. And in particular, you'll see on the 25th of August, we have this intensification of the magnetic spherical ring current and then a slow decay again. That's one of these magnetic storms. We also see some subtle differences between the different satellites. That is because the satellites measure the Earth's magnetic field at different local times. So if we now combine the data from all these satellites, then we are able to look at the space-time structure of a magnetic spherical ring current, where we see that by far the largest part is due to symmetric ring current, but we also have deviations from this symmetry, in particular during geomagnetic storms. This is the first time that it was possible to estimate the time-space structure of a magnetic spherical storm using simultaneous measurements from different satellites. Another application is in the core field. What you see here is the acceleration, so that means the second time derivative of the radial magnetic field at the surface of the core. That means at depth of 3,000 kilometers approximately. This is for one specific time instance, it's for 2050. And let's now focus on the equatorial belt. And let's look at how does the magnetic field change in time in this equatorial belt. So what we see here is for the last 20 years, how this has evolved. The first 10 years is based on CHAMP. The last 4 years or so are based on SWARM. But then we have this gap of 3 years without any data. On the left-hand side, this is based on a model. So it's based, and that's a smooth version. It's mainly some interpolation over time, also guided by a few observations from magnetic ground observatories. But if you now include CryoSat, and on the right-hand side, you see point estimates of the second time derivative. And then it's obvious that CryoSat really can contribute to infer what's going on in this 3-year gap. How, And finally, that is an application regarding the magnetic field of the oceanic M2 type. So it's a tiny magnetic field variation. It's well below 2 nanotesla. Remember that the Earth's magnetic field has a strength of 50,000 nanotesla, and the measurement error is about 6 nanotesla. Still, we can extract this information from CryoSat because of statistics, because we exactly know what is the period of the ocean tide. And we have done that here on the left-hand side. That's based on 10 years of observations, magnetic observations from CryoSat. So it's the M2 tide. It's the magnetic signal of the oceanic M2 tide. What's going on here is tides means we have movement of seawater. Seawater is an electrical conductor. So that means we have movement of an electrical conductor in a magnetic field, Earth's magnetic field. That produces an electric current, and an electric current produces a secondary magnetic field. And it's this secondary magnetic field that we can observe with CryoSat. The left-hand side, these are the observations. On the right-hand side, it's a model prediction based on a model of the ocean tidal flow, model of conductivity of the mantle for the lithosphere and seawater. And you see a really good agreement between those two. So in summary, yes, CryoSat has actually set a new standards of what is possible with navigational magnetometers. We have never seen before a satellite with that high magnetic data quality. Of course, apart from dedicated satellite missions like SWARM. There's enormous potential for science and applications, also regarding space weather. These calibrated data until now are freely available, and we are now preparing for an operational calibration and provision of CryoSat data, for instance, in batches of 1 month length. And with that, I would like to thank you. And you can see how we can now combine data from SWARM with other satellites. Thank you.
Thank you, Niels. That was very, very impressive. So Jerome made a comment. Yes, impressive work and nice talk, indeed. Jerome put a link to the CryoSat magnetometer data. Says maybe a future swarm or CryoSat magnet-based tidal model, forced aliasing or aliasing altimetric data. I'm not entirely sure what he's saying. Maybe you can comment a bit on that, Niels. Oh, de-aliasing. Perhaps the tidal model with using the magnetometer data.
Yes, and well, I think what we in particular could do with this combination is we have a tidal signal not only from the oceans but also from the ionosphere. So by combining data from different local times, we hope that it will be possible to distinguish what part of the tidal signal is due to the oceans and what part is due to the ionosphere. Because with satellites, unfortunately, also, and the ionosphere is below. That means it's an internal source, like the ocean. So that's our hope for the future.
All right. Thanks again, Niels.
Just let me thank you, because it's been a very nice lesson on what CryoSat can do above any of the expectations, and it was very well designed, thought, and developed, and the data that is providing is clearly amazing, and you've just given another proof of that. So thanks a lot.
That wraps up our session. Thanks everyone for joining us.
Session is over. I guess see you later. Thanks, Nathan.
Thanks, Monica.
Those who are still here, Richard has written something on the chat that they had problems during the procurement of those magnetometers. They're commercial products, and we needed to modify them during the production. Our guy who spent weeks trying to get it right would be gratified.
Yes, and I would like to get in contact with these people doing that, because perhaps we can learn even more about what's going on CryoSat with the magnetometers.
Maybe Richard could put you in contact with them. Richard Francis. Okay, bye-bye everyone. See you on the next session.
Okay, so we